For centuries, the solar system looked simple. A star, 8 planets, maybe a dwarf planet or 2 tacked on at the edge. But the closer our spacecraft have come to those small, dark objects, the more that picture has fallen apart. We have watched probes drift through the dusty atmospheres of comets and measure gases that have drifted unchanged since the solar system was young. We have seen rubble pile asteroids that behave more like loosely held clouds of boulders than solid rock. We have brought microscopic grains of comet and asteroid material back to laboratories on Earth and discovered that they are rich in water-bearing minerals and complex organic molecules. Each of these encounters has answered one question and opened 5 more. We still do not know precisely how the very first solid bodies emerged from the swirling gas and dust around the infant sun. We do not know how many different families of small bodies exist, hidden in the dark beyond Neptune, or how many flavors of water and organics they carry. We are only beginning to understand how often these objects strike young planets, how much they shape atmospheres and oceans, and how strongly they influence whether a world becomes dry and airless or habitable. Even the Earth, our map is incomplete. This video begins from that uncomfortable, exciting place, standing at the edge of what we know. We will ask, what are the biggest open questions about small bodies in our solar system? Which mysteries of water, organics, and planet formation they still hold? What new missions and telescopes are being built right now to explore them? And what all of this might mean for planets, and possibly life, around other stars. We are used to thinking of maps as finished things, coastlines inked in, mountains named, oceans labeled. We are not at the end of the tale of small worlds. We are at the beginning of understanding just how central they are to the past, present, and future of planetary systems. In this part of the journey, we turn the telescope around and look straight at our own ignorance. We have flown past comets, orbited rubble pile asteroids, dived into the Kuiper belt, and brought dust home in carefully sealed capsules. Yet some of the most basic questions remain stubbornly open. Where did Earth's water really come from? How common is complex chemistry in small bodies? How did the first solid worlds begin to assemble from dust? And is our own architecture of belts, clouds, and Trojans a cosmic norm, or an odd exception? These questions all live in the same place, in the small, cold, dark bodies we have only just begun to understand. One of the simplest questions, where did Earth's water come from? Turns out to be one of the hardest. Early Earth was a hot, violent place. Some water may have been present from the very beginning, bound in minerals in the growing planet. Some was likely lost during the most energetic impacts. To rebuild the oceans we see today, something had to deliver additional water and volatiles after the worst of the chaos settled. For a long time, comets seemed like the obvious answer. They are literally flying ice. But when we started to measure the hydrogen isotopes in cometary water, the ratio of deuterium to ordinary hydrogen, we found a more complicated picture. Many well-studied comets, especially from the distant Oort cloud, have deuterium ratios roughly twice that of Earth's oceans. Some Jupiter family comets come closer, but overall the match is not clean. By contrast, certain carbonaceous meteorites, believed to come from water-rich asteroids similar to Bennu or Ryugu, have hydrogen isotope ratios that line up more naturally with terrestrial seawater. Today, the leading view is that carbonaceous asteroids supplied a large fraction of Earth's water, with comets playing a secondary, mixed role. But leading view is not case closed. We have detailed isotopic measurements from only a limited number of comets and meteorites. We are just beginning to analyze the samples returned from Ryugu and Bennu. The true contribution of each population, different asteroid families, different comet reservoirs, remains an active, quantitative puzzle. It may be that Earth's water story is not dominated by a single source, but by a tapestry of deliveries over tens of millions of years. The same uncertainty surrounds chemistry. We now know that comets and primitive asteroids can carry an impressive catalog of organic molecules, simple alcohols, aldehydes, nitriles, even amino acid, like compounds and complex, tar-like macromolecular organics. Missions like Rosetta, sample return analyses, and laboratory studies of meteorites have collectively shown that rich organic chemistry flourishes in cold ices irradiated by ultraviolet light and cosmic rays. But how representative are the few objects we have sampled? We have detailed molecular inventories for only a tiny subset of comets and a handful of returned or meteoritic samples. For most small bodies, our knowledge comes from low-resolution spectra that tell us which broad functional groups are present, not the full set of molecules or their relative abundances. Open questions stack up quickly. How varied are the organic inventories of comets from different regions? Jupiter family comets compared to long-period comets, or classical Kuiper belt objects compared to scattered disk bodies. How often do we see nitrogen-rich organics, sulfur-bearing species, or halogen-containing molecules that might influence prebiotic chemistry in subtle ways? Do most icy bodies evolve toward a similar dark, red, organic-coated endpoint, or are there distinct chemical families we have not yet recognized? At the moment, our chemical map of small bodies is like an atlas with a few detailed insets and vast, blank regions in between. Beneath that chemical uncertainty lies an even more fundamental unknown. How did the very first solid bodies form in the protoplanetary disk? Classical pictures imagine dust grains colliding and slowly sticking, growing from micrometer-sized particles to pebbles, boulders, and finally planetesimals. But simple collision models show a problem. Beyond a certain size and speed, impacts tend to fragment rather than grow aggregates. Over the last 2 decades, new models have suggested that aerodynamical processes in the gas disk, such as streaming instabilities, could concentrate centimeter-scale pebbles into dense clumps that collapse gravitationally into kilometer-scale bodies in one step. Objects like Arakoth, with its gently fused lobes and mounded, low-energy appearance, seem to support this pebble cloud collapse view. Some rubble pile asteroids, with their loosely bound aggregates, point in a similar direction, gentle assembly, not relentless, high-speed smashing. But again, our sample is tiny. We have only a few high-resolution case studies that preserve very early structure. We do not yet know whether this gentle assembly mechanism operated everywhere, or whether the inner disk, closer to the Sun and hotter, followed different paths than the icy outskirts. Did planetesimals in the region that built Earth and Mars form the same way as those at 45 astronomical units, or did multiple formation channels coexist? The answer is written into the internal structures and size distributions of small bodies throughout the solar system, but we have barely started to read that script. Zooming out even further, another question looms. How typical is our architecture of small bodies in the broader galaxy? We know our own system hosts an asteroid belt between Mars and Jupiter, dense Trojan swarms flanking Jupiter's orbit, a broad Kuiper belt beyond Neptune, and a much more distant Oort cloud of icy bodies. We have glimpses of similar structures in other systems, warm dust belts seen in infrared around some stars, hints of cold debris belts farther out, possible Trojan-like co-orbitals inferred from subtle signals. But we are far from a complete census. Are asteroid belt, like structures, common outcomes of planet formation, or do they require fine-tuned histories of migration and scattering? Do most planetary systems carve out broad comet reservoirs like our Kuiper belt and Oort cloud, or are ours unusually massive or unusually long-lived? Without direct images of individual small bodies around other stars, we infer their presence from indirect signatures, excess infrared light, transient dips in starlight, or, in rare cases, interstellar visitors that wander through our own skies. That brings us to perhaps the most humbling unknown of all. What are we missing entirely? Our telescopes cannot yet see every small near-Earth object. Very small, very dark bodies slip below the detection thresholds of current surveys. In the outer solar system, countless faint trans-Neptunian objects likely remain undiscovered, especially beyond the traditional Kuiper belt. The detailed population of the inner Oort cloud is still a theoretical construct, not an observed catalogue. And between the stars, there is almost certainly a vast population of ejected planetesimals, like Oumuamua and 2Ir Borisov, that pass through the inner solar system without ever crossing a camera's field of view. In other words, even within our own backyard, our inventory of small bodies is incomplete. The objects we know, Bennu, Rigu, 67P, Arakoth, Psyche, the Trojan targets of Lucy, are not the whole story. They are the first well-lit islands in a much larger, still dark archipelago. What we do know is that every time we fill in one patch of that map, new questions appear at the edges. Each mission answers a few specific questions and then hands us a larger set of why, and how often, and what else is out there. That is what makes small bodies such powerful scientific frontiers. They are at once the most ancient archives of the solar system and the most active generators of new mysteries. In this episode, we gather those open questions into a single constellation. We still do not know the full story of Earth's water. We still do not know how diverse cometary chemistry can become. We still do not know whether pebble cloud collapse is the universal language of planetesimal formation, or just one dialect among many. And we still do not know how typical our belts, clouds, and swarms are among the planetary systems scattered across the Milky Way. What we do know is that the path to those answers runs through small worlds, through more sample return missions, deeper surveys of the outer solar system, sharper spectra of faint comets, and, someday, perhaps, new explorers sent to the dark edges of the map where our models are weakest. The frontier is not empty. It is full of questions, written in ice and rock. For most of human history, small bodies were distant specks and brief streaks of light. Now we are in a different era. Missions that are already flying, and others still on the drawing board, are aimed directly at the questions we still cannot answer about asteroids, comets, and the chemistry that built our world. Over the next few decades, these spacecraft will turn unknowns into data. The first cluster of missions is driven by a very practical motive: planetary defense. After the DAT impact on Dimorphos, the obvious next step is to measure exactly what we did. ESA's Hera mission is designed for that. Launched toward the Didymos Dimorphos system, Hera will arrive years after the DAT impact, when the dust has settled and the binary has returned to a calmer state. From close orbit, it will map the impact site in detail, measure the size and shape of the crater, and reconstruct how much material was excavated and where it fell back. Hera will not travel alone. It will deploy small companion probes that will fly even closer, performing fine-scale imaging and radioscience experiments to measure the density and internal structure of Dimorphos. Together, the main spacecraft and its CubeSat partners will turn DAT from a one-time demonstration into a calibrated experiment. For the first time, we will be able to connect an impact we made on a small body with high-precision measurements of how its orbit, mass distribution, and surface actually changed. Those numbers will feed directly into future deflection designs, transforming planetary defense from educated guesswork into engineering. Finding the objects that matter is just as important as knowing how to nudge them. That is the purpose of dedicated near-Earth object survey missions, such as NASA's planned NEO Surveyor. Instead of relying only on visible light from ground-based telescopes, NEO Surveyor will use infrared detectors in space to look for the faint warmth of dark, Earth-approaching asteroids. Many of the most dangerous objects are charcoal black and only a kilometer or a few hundred meters across. They reflect little sunlight but still glow faintly in thermal infrared. By scanning large swaths of the sky, night after night, an infrared surveyor can uncover thousands of previously unseen NEOs and measure their sizes far more accurately than visible-only surveys. The goal is straightforward but ambitious: to identify the vast majority of potentially hazardous asteroids large enough to cause regional or global damage, and to do so early enough that slow, gentle deflection options remain on the table. Every orbit refined, every dark rock moved from unknown into tracked, shrinks the domain of unpleasant surprises. A second group of future missions focuses on comets, the most volatile-rich, chemically complex small bodies we know. Here, one of the most innovative concepts is ESA's Comet Interceptor. Instead of targeting a specific comet years in advance, Comet Interceptor will be launched to a gravitationally stable point near Earth and simply wait. When ground-based surveys discover a suitable target, a long-period comet falling toward the Sun for the first time in millions of years, or even an interstellar visitor, Comet Interceptor will depart on a fast flyby trajectory. The spacecraft will actually consist of several elements, a main bus and one or more smaller probes. As they approach the comet, they will diverge slightly, sampling different parts of the coma and approaching the nucleus from different angles. The scientific payoff is clear: a pristine nucleus that has not been repeatedly baked near the Sun, carrying ices and organics that still resemble those in the outermost parts of the protoplanetary disk. Where Rosetta followed a single short-period comet over time, Comet Interceptor aims to strike once, quickly, at an object that preserves an even earlier state of the solar system. Beyond that, space agencies are studying concepts for new comet orbiters and landers that would build on Rosetta's legacy with more sensitive mass spectrometers, dust collectors, and microscopes. The goal is to move from what molecules are present, to how do they vary from place to place, and how are they organized in the ice and dust. These next-generation missions would treat a comet not just as a source of spectra, but as a three-dimensional chemical landscape. A third group of missions continues the systematic exploration of asteroids and other small bodies. Some of these spacecraft are already flying. NASA's Lucy is on its long tour of Jupiter's Trojan asteroids, treating them as fossils of the early outer solar system. NASA's Psyche is cruising toward a large, metal-rich asteroid that may preserve material from deep inside a disrupted protoplanet. ESA's Hera, in addition to its planetary defense role, will also refine our understanding of how rubble pile asteroids respond to impacts. Each of these missions targets a different population, but together they ask the same question. How many different kinds of small worlds did planet formation produce? Looking further ahead, mission concepts are being developed for sample return from ever more exotic targets. A metallic asteroid sample return mission would let us hold, in a lab, material that may be analogous to planetary cores. Main belt comets, bodies on asteroid-like orbits that occasionally sprout comets, are prime candidates for probing the boundary between dry asteroids and wet comets. Sample return from such an object could tell us how much frozen water is hidden inside what look, from far away, like ordinary rocks. Farther out still, scientists imagine missions to collect material from Kuiper Belt objects or to skim dust from the outer solar system, bringing home tiny fragments of worlds that orbit tens of billions of kilometers away. These concepts are technologically demanding, but the logic is the same as for Bennu and Ryugu. Every time we bring a piece of a small body into a clean terrestrial laboratory, we multiply what we can learn by orders of magnitude. Even missions that are not primarily about small bodies will shape this frontier. Mars Sample Return, for example, is being designed to retrieve cores drilled and cached by the Perseverance rover. Its architecture, precision landing, sample pickup, ascent into orbit, rendezvous with an orbiter, and sealed return to Earth, will serve as a template. Once we know how to do this reliably at Mars, the same basic playbook can be adapted, over time, to more distant targets, complex asteroids, comet nuclei, and perhaps even the surfaces of icy moons. In that sense, the next few decades are not just about individual spacecraft names. They are about building a toolkit, precise impactors and detailed follow-up missions for planetary defense, infrared surveyors that finally close the catalog of nearby small bodies, agile interceptors waiting to pounce on pristine comets, and robust sample return systems that can be aimed at almost any solid surface in the solar system. Each new probe moves small bodies a little further from the realm of the unknown and a little closer to something we can model, measure, and, when necessary, manage. In the background, large observatories, on the ground and in space, will expand the targets list. Whitefield surveys will discover new near-Earth objects and distant trans-Neptunian bodies. Infrared telescopes will refine their sizes and albedos. Together, telescopes and spacecraft will create a feedback loop: discovery, selection, encounter, and then deeper understanding, feeding back into better models and better surveys. From a distance, these missions can look like isolated projects. One spacecraft to a Trojan, another to a metal-rich asteroid, a third waiting for a never-before-seen comet. But viewed together, they are the early phases of a long-term campaign. The goal is simple to state and difficult to achieve: to map and understand the small bodies of our solar system well enough that we can read in them the history of planet formation, the pathways of water and organics, and the risks and opportunities they pose for a technological civilization. We are still at the beginning of that effort, but for the first time, we have a clear sense of where the next steps will fall. In the coming decades, our view of small worlds will depend as much on our telescopes as on our spacecraft. Probes like Lucy, Psyche, or OSIRIS-Rx can dissect a handful of targets up close, but to understand how those few examples fit into the wider population, we need observatories that can see thousands or millions of objects at once. Future space telescopes and all-sky surveys are, in a very real sense, the context cameras for everything we have learned in this series. High above Earth's warmth and weather, the James Webb Space Telescope is already changing how we study small, cold bodies. Its segmented mirror and ultra-sensitive infrared instruments are designed to pick up faint heat from objects that shine only weakly in reflected sunlight. For comets, centaurs, and Kuiper Belt objects, that infrared glow is a treasure trove of information. By measuring their thermal emission, JWST can estimate sizes and albedos more accurately than optical data alone, separating small and bright from large and dark. In its spectra, narrow absorption features betray the presence of specific ices and minerals on distant surfaces and in cometary comets, water ice, carbon dioxide and carbon monoxide ices, traces of methane, methanol, and other carbon-bearing species that hint at complex organic chemistry. This is not just a catalog of ingredients. When we compare the spectra of different populations, a comet diving in from the Oort cloud, a Kuiper Belt dwarf planet, a centaur in a transitional orbit, we start to see patterns in how chemistry depends on formation zone, thermal history, and exposure to sunlight. JWST also looks outward, beyond our own system, at protoplanetary disks and debris belts surrounding young stars. There, in the same infrared bands, It measures ices and dust in other planetary nurseries. That bridge between our comets and their disks lets us ask whether the raw materials we find in Bennu, Ryugu, or Arrokoth are typical or unusual compared to the galaxy at large. Closer to home, the Vera C. Rubin Observatory will give us something we have never had before, a moving, evolving map of the dynamic sky. Its Legacy Survey of Space and Time, LSST, will repeatedly image the southern sky over roughly a decade, recording how every detectable point of light changes night after night. For small bodies, that cadence is revolutionary. Faint near-Earth asteroids that appear as short streaks in a single exposure will be picked up in multiple visits, allowing their orbits to be reconstructed even when they are only a few hundred meters across and dark as charcoal. In the outer solar system, LSST will fill in the architecture of the Kuiper belt and scattered disk with unprecedented detail. By detecting and tracking large numbers of trans-Neptunian objects, it will refine the distribution of orbits in different dynamical classes: cold classicals, resonant objects, scattered and detached populations. Subtle features in that orbital structure, clusters, gaps, preferred inclinations, encode how Neptune migrated, how early gravitational encounters unfolded, and whether any unseen massive perturbers might still lurk far beyond Pluto. Light curves from repeated observations will reveal rotation periods, shape hints, and binary systems, turning faint points of light into physical objects with spin and structure. Rubin's survey will also transform planetary defense. Today's catalog of potentially hazardous near-Earth objects is incomplete, especially for smaller, darker bodies that are hardest to spot from the ground. A wide-field, deep, and frequent survey from a single, powerful facility will dramatically shrink the population of unknown impactors. Combined with dedicated infrared survey missions that specialize in detecting warm, dark objects against the cold background of space, LSST-type data will give us not only better statistics, but earlier warning and more accurate orbits for bodies that pass near Earth. Other observatories complete the picture. Large ground-based telescopes with adaptive optics and high-resolution spectrographs can take a subset of the objects Rubin discovers and examine them in far greater detail. For brighter comets and dwarf planets, they can resolve surface features, measure subtle variations in composition across a disk, and track how gas production changes with time. Time series photometry from these facilities can uncover binary asteroids, fast rotators, and objects whose changing brightness betrays irregular shapes or tumbling motion. Every such measurement adds another piece to the story of how collisions, spin-up, and tidal interactions reshape small bodies over billions of years. Future space telescopes will push these capabilities still further. Next-generation infrared observatories are being designed with even higher sensitivity and sharper vision than JWST in some bands, allowing them to detect smaller and more distant Kuiper belt objects and perhaps trace tenuous dust structures beyond the main belt of known trans-Neptunian objects. Ultraviolet or X-ray missions can study how the solar wind and high-energy photons interact with cometary Comean surfaces, altering chemistry over time. For planetary systems around other stars, upcoming missions will resolve debris disks with finer structure, catching analogs of asteroid and Kuiper belts in the act of colliding, grinding, and feeding material into planet-forming zones. Together, these eyes on the sky turn our handful of close-up case studies into part of a coherent whole. Spacecraft like Rosetta or OSIRIS-RX can tell us exactly what one nucleus or one rubble pile is made of, Rubin, JWST, and their successors tell us how representative that object is, how many cousins it has, and where they all fit in the larger architecture of the system. Surveys flag the outliers, unusually red centaurs, highly inclined KBOs, near-Earth asteroids with strange orbits, and missions can then be designed to visit the most intriguing targets. In that sense, telescopes and spacecraft are partners. One provides the wide, statistical view, the other delivers the close, physical truth. As we look ahead, the combination of deep surveys, sensitive infrared spectroscopy, and targeted missions promises to turn today's rough sketches of the small body populations into a detailed atlas. We will not just know that there is an asteroid belt and a Kuiper belt, we will trace their internal substructures, their families and fractures, their quiet members and their escapees. On top of that, by watching similar belts form and evolve around other stars, we will finally be able to place our own chronicle of small worlds in a broader cosmic context. One planetary system among many, each with its own architecture of rock, ice, and dust. When we talk about small bodies as the frontier, It is tempting to think only about the places we have already reached, asteroids we have orbited, comets we have landed on, Kuiper belt objects we have imaged in passing. But over the last decade, two faint visitors have reminded us that the map is much larger than the Sun's own family. They came in fast, on paths that could never be bound to our star, and then they left again. Each was a brief warning. There is a whole traffic of small bodies between the stars, and we have barely begun to see it. The first was 1I Oumuamua, discovered in 2017. At first it looked like any other small, dim object in survey data. Then orbital calculations made it clear that its path was hyperbolic. Instead of looping around the Sun, it would swing past once and never return. Its speed and inbound direction could not be explained by any origin inside the solar system. Oumuamua was the first clearly identified interstellar object, a fragment from another planetary system, passing through ours by chance. The more astronomers looked, the stranger it became. Its brightness changed dramatically as it rotated, implying a very elongated or flattened shape, unlike any asteroid we have seen up close. It showed no obvious coma or tail, yet its trajectory included a tiny but measurable non-gravitational acceleration, as if something were gently pushing it. One family of explanations invokes extremely low-level outgassing of volatiles that did not produce a visible coma. Another suggests that an unusual shape and very low density could make it sensitive to sunlight in ways we do not usually see in solar system rocks and ice. None of the hypotheses is entirely satisfying, and that is the point. With just a few weeks of good data and no spacecraft nearby, Oumuamua has remained an open question. 2 years later, in 2019, a second messenger arrived, 2IR Borisov. Where Oumuamua was enigmatic and almost asteroid-like, Borisov was immediately, unmistakably a comet. It had a coma, a tail, and the classic behavior of an icy nucleus warming as it approached the Sun. Once again, its orbit was hyperbolic, clearly marking it as an interstellar visitor rather than a long-period comet from our own Oort cloud. Spectroscopic observations of Borisov's coma revealed a composition that was both familiar and extreme. The same kinds of volatiles we know from solar system comets were present: water, carbon monoxide, and other common gases, but the relative abundance of carbon monoxide was unusually high. That points to an origin in a very cold region of its home system, where CO ice can be preserved efficiently. In other words, Borisov looked like a comet that could have formed in the cold outer zones of almost any planetary system, including ours, but pushed toward the more volatile-rich end of the spectrum. It told us that the chemistry of comet-like bodies elsewhere in the galaxy may rhyme with, rather than completely differ from, the chemistry we know. From just these two objects, astronomers have been able to estimate that interstellar debris, relics of planet formation and long-term gravitational scattering, is probably far more common than we once believed. For every Oumuamua we manage to spot, there may be thousands of similarly sized bodies passing through the inner solar system over geological timescales, just too small and faint for our current surveys to notice unless the geometry is favorable. Most will never come close enough, or be bright enough, to appear in our catalogs. Our picture of the interstellar background is therefore based on a handful of pixels and a great deal of inference. The natural next step is obvious and bold: do for an interstellar object what we have done for comets and asteroids in our own system. Not just watch from a distance, but send a spacecraft to meet one. Concepts under study imagine a probe waiting in an inner solar system orbit, fueled and ready, until sky surveys flag a newly discovered hyperbolic object bound for a close passage. The spacecraft would then launch or maneuver onto an intercept trajectory, flying by at high speed to image the nucleus, sample its gas and dust, and perhaps even return a tiny amount of material to Earth. The technical challenges are severe: short warning times, very high relative velocities, and limited opportunities to correct course, but the scientific payoff would be unprecedented. Such a mission would turn interstellar visitors from curiosities into data-rich probes of other planetary systems. Does the dust on their surfaces resemble the grains we see in comets here, or are the mixtures of ices, organics, and minerals systematically different? Are their densities and internal structures similar to our rubble piles and icy nuclei, or do other systems produce a different mix of solid bodies? Do their volatile inventories hint at the temperature structure of the disks where they formed, or at migration histories very unlike our own? Each interstellar object would carry a chemical and dynamical biography written in its composition and orbit. Even without a dedicated interceptor yet, the next generation of surveys will change the game. Telescopes that repeatedly scan the whole sky, night after night, will catch more fast-moving, faint objects that do not follow solar system-bound paths. Over time, a statistical sample of interstellar visitors, even if each is only observed from afar, will tell us how common they are, how their sizes and brightnesses are distributed, and whether Borisov's CO-rich chemistry is typical or an outlier. At that point, small bodies truly become messengers on a galactic scale. We will no longer be limited to sampling the leftovers of our own planet-forming disk. We will be able to compare those leftovers with debris from stars scattered across the local spiral arm. If the organics and ices in interstellar comets look broadly similar to what we see here, it will support the idea that the basic chemical ingredients of habitability are widespread. If instead we find whole families of compositions that have no close analog in our system, we will learn that planetary systems can take very different chemical paths even when they obey the same physical laws. In that sense, interstellar visitors are the purest expression of what small bodies have always been in this series, archives in motion. An asteroid family in the main belt records the history of collisions around our sun. A Trojan swarm preserves traces of giant planet migration. A Kuiper belt contact binary remembers how the first planetesimals came together. An interstellar comet or asteroid carries the same kind of memory, but from somewhere else entirely. To catch one up close would be to hold, for a moment, a fragment of another system's story in our hands. We began with a simple picture, the solar system as a set of neat, bright circles around the sun planets, named and familiar, following their paths like clockwork. But as we turned our attention to the smaller things, the dust, the rubble, the icy fragments in the DAC, that picture changed. It became less like a diagram and more like a living archive. We followed grains of dust that froze into comet nuclei at the edge of the young disk, and then, billions of years later, flared into spectacular comi when they returned to sunlight. We watched rubble piles like Itokawa, Ryugu, and Bennu reveal that asteroid does not mean solid rock, but fragile agglomerations held together by gravity and time. We saw Trojan swarms marching beside Jupiter, not as background clutter, but as fossil fleets preserving the era when the giant planets were still wandering. We stepped beyond Neptune into the Kuiper belt, where worlds like Arakoth, cold and slow, keep the shapes of the very first planetesimals almost untouched. With each step, the theme repeated: small bodies remember what larger worlds forget. Planets resurface themselves, melt, differentiate, grow atmospheres, and erase much of their own childhood. But fragments, from cometary grains down to specks in a return sample capsule, carry isotopic ratios, mineral structures, and organic residues that trace back to the first tens of millions of years. In those numbers and spectra, scientists read when and where water condensed, how far solids drifted, how often collisions shattered or gently merged the building blocks of planets. Seen this way, each asteroid, comet, and icy remnant becomes a page in a diary written by the solar system itself. Impact craters are the punctuation marks, organizing the story into chapters of bombardment and calm. Isotopes are the accent in the language of formation, distinguishing inner disk material from outer disk immigrants. Organic molecules are the early sentences that foreshadow biology, not life, but a vocabulary of carbon chemistry that made life possible on at least one world. What missions have done in the last few decades is to open that diary for the first time. Sample return capsules landing in deserts. Orbiters mapping rubble piles stone by stone. Landers touching down on cometary cliffs. Once, these objects were just points of light on photographic plates. Now they are places with terrains, histories, and open questions. We can weigh them, drill into their chemistry, and trace their trajectories from the quiet outskirts of the disk to violent encounters with young planets. And yet, for every small body we have visited, there are millions we have only inferred, and countless more we have never seen at all. The main belt is still full of families we have never mapped in detail. The Kuiper belt stretches outward, faint and incomplete in our catalogs. Interstellar objects cross our sky so quickly that we barely recognize them before they are gone. The chronicles we have read so far are only a few pages torn from an enormous, unfinished volume. The deeper message is simple and humbling. We used to think of small bodies as leftover debris, the crumbs swept to the edge of the planetary table. Now we know they are the archives of everything that happened before a planet like Earth could have oceans, continents, and living cells. They remember the temperature of the nebula, the dance of migrating giants, the timing of bombardments, and the spread of water and organics across newly formed worlds. New missions will launch. New telescopes will open their mirrors to the sky. They will find darker NEOs, colder Kuiper belt objects, stranger comets, and perhaps more interstellar wanderers. Each one will add a line, a paragraph, a new chapter to this ongoing record. The chronicles of small worlds do not end when the credits roll. They expand every time we discover, model, or sample another fragment in the dark. Out there, beyond the orbit of Mars, beyond Jupiter's Trojan swarms, beyond the pale ring of the Kuiper belt, small bodies continue their slow, intricate choreography. They collide, drift, evaporate, accrete, and sometimes fall inward toward a blue planet that has just begun to understand what they mean. We are latecomers to their story, but we are also, now, its readers. And as long as we keep asking questions about water, about chemistry, about how many ways there are to build a world, those readers will keep turning pages. The smallest objects in our solar system will go on doing what they have always done, quietly carrying the memory of how everything began.